Guys, welcome to the next lecture. Today, I am moving on from relations to functions. Relations and functions, they are the essence of mathematics. They are extremely important part of algebra. Relations and functions are something, see, once you understand relations, you can actually talk about functions. And functions are such an integral part of any branch of mathematics, be it economics, be it physics. Everything that you work upon, you create a function and then you analyze it. Functions and relations are the one of the most important topics in algebra. It's very important to be able to identify what relations are a function and what are not. Yes, what I'm trying to tell you here is a function is definitely a relation. What relation does? Relation relates to sets or elements or things which are there in the sets, right? Hence, relation is a subset of an ordered pair or the Cartesian product. We say that R is a subset of A cross B, where A and B are two sets which are getting related to each other. A is related to B, right? So A gives you an input, and once the relation is applied, you get an output. So you have first element and another second element. That means you have an ordered pair. We have spoken about all that, right? So R is the set of ordered pairs. Pairs like, you can have 1, 1, you can have, say, 1, 2, you can have relation 0, 0, you can have a relation 0, 1. That's how I can define my relation set. It's a set of ordered pairs. And by now, we know the importance of ordered pairs, right? And in an ordered pair, in terms of relation, if I talk about, you have an input, and after applying the relation, an output gets generated, right? So historically, if I may just, hint upon what functions and how relations and functions came into existence. So it was, I think, around what I read, around 17th century. Few mathematicians work on it, and then improvisations happen. A very famous mathematician, Rene Descartes, he talked about many mathematical relations. The term function, according to what I read, was given by Leibniz. I'm sure, very familiar with the name Leibniz. So you have Leibniz rule and etc. in calculus. So he gave the term functions. It is said that he gave the term function, and he spoke about y equals to x, dy by dx, and so on and so forth. Then another improvisation that happened was notationally writing function. Function is written as y equals to fx. That means you are giving the input x and getting an output y. This came into existence by Euler. Again, a very famous mathematician. So he introduced this concept of y equals to fx in 1734 around. It is said that Dirichlet gave the modern definition of function. He provided the definition that if a variable y is so related to a variable x that whenever a numerical value is assigned to x, there is a rule according to which a unique value of y is determined. Then y is a function of independent variable x. And yes, that's the definition that we actually take up for function. I will now talk of two simple examples for relation, and then later on we will try to see that are these relations, can we call them functions once we formally define function. So the relation, say, mother of. So M is a mother of, say, she's got two sons, so S1 and S2. Hence, the ordered pair that you will see here will be M comma S1, because M is a mother of S1. The moment you will write S1 comma M, there will be a problem, because that would be saying that S1 is a mother of M. But that's not the case, right? So ordered pairs that I get from here is M comma S1 and M comma S2. simply gives you that M R S1. That means M is a mother of S1. M R S2. That means M is a mother of S2. A relation could be, for example, rating your choice of fruits. Suppose the availability is that you have apple, bananas, oranges, pineapple, and guava available to you. According to your preference, you can rate them from, say, 1 to 10. If you give 10, so that means it's your favorite, 10 on 10. So if I say A gets the rating 10, I love apples. So yeah, so from my side, apple is a 10 pointer. I like banana, but not that much. 6 is what I'll give it as a rating. I love oranges, so I'm going to give it a 10 again. Pineapple, yeah, I like them, but not as frequently. I take it as probably an orange. Guava, not of my preference at all, so I'm rating it 4. The ratings, basically, I'm giving it a score out of 10. Bigger the score, better it is, right? For me, my preference. So what is happening is that I have certain input. My input are the fruits, A, B, O, P, G. These are your inputs. A set that consists of all your inputs, possible inputs, it's actually called a domain. So this is the domain for my relation. The score could be anything from 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All these can be the score. Well, I have written my rating. So A gets a 10. So A goes to 10. B goes to 6. O goes to 10. P goes to 8. And G goes to 4. Okay. So this set that you can see here, the set that consists of possible outcomes, there's a name to that set. And the name is codomain. It is supporting this domain and it's called the codomain. Okay. Then what you would realize is that your actual outcome are the ratings that I have given: 10, 6, 10 again, 8, 4. I may write 10 again. I may not write 10 again because it's the same number. But this is your actual outcome. And the set of actual outcomes is called range. The set of actual outcomes is called the range for any given relation. These are the terms which are common for relation also in function also. You will realize it very soon, and we'll be in detail talking about these terms. This was about relation. I just gave you certain examples. Now let's talk about the idea of function. The idea of function is exactly like you have a machine and input goes in and output comes out. Something happens in that machine. What can happen? Maybe the input that you put, X, the machine is squaring it. So if you put 2, you get 4. You put 3, you get 9. Or maybe it is just merely doubling it. You put 2, you get 4. You put 3, you get 6. Or maybe it is making half of it. So if you put in 4, you get half of it, and so on and so forth. Okay. This machine can operate in any way, and it is a function. What you will be saying is that you have an input and you apply the function on it and you are getting an output. So the output is a function of your input. Hence, function also relates input and output. So your question should be that then why do I have another terminology, functions? Why not just call it a relation? The thing is that function needs to provide you an output or outcome which is unique in nature. So when you put 2 as an input, you get a unique value 4. When you put an input 3, you get a unique value 9. That's what is very, very important. So when we define function, it is a relation. Indeed, it's a relation. A function f between a and b is a relation between a and b, which means if I say this function is f, F is also a subset of A cross B because it is a relation. But it's got to satisfy 2 points such that, number one, the first point is that for every input that I have in A, so when I say A cross B, input cross output. So input is what you have in A. From A, you are putting in the first element that you have in the ordered pair. That's the input, right? So for every X in A, there is an element Y belonging to B such that X comma Y, the ordered pair, belongs to F, just like you write in relation. Or X is related to Y, or Y is equal to Fx. So that's basically, we are saying that every input in A must have an output. You cannot just put something in the machine and nothing comes out. No, that cannot happen. So when you put something in the machine, something has to come out, okay? And this output that you are getting, that should be unique. This output Y should be unique. That is, X comma Y belongs to F and X comma Z belongs to F. If this is happening, then Y and Z have to be the same. You cannot have two outputs coming out of the same input. That's extremely, extremely important. And this is how a relation differs from functions. Can you say mother of is a function? No, because here we have seen that this mother has two sons. So what is happening? One input is giving you two outputs. No, that cannot happen in a function. So this is a relation, but it's not a function. Rating of your choice of fruit. I gave the same rating to two fruits, A and O, that is orange and apple. They both are 10 for me. Is this a function? Well, yes. The score of 10 is unique for A and the score of 10 is unique for O. It's not that I'm giving, in this relation, I will not give two scores to the same fruit. It's not sensible, right? So when I'm rating, I'm saying apple is a 10 for me. Why would I say apple is a 5 for me, right? It's a unique value that I'm giving to apple. Similarly, it's a unique value I'm giving to orange. So indeed, actually, this relation is a function. The previous one, mother of, is not. Say y is equal to x squared. If you graph it, the first thing probably you can do is you can just graph it. X squared is a simple graph. We know that, it's going to move symmetrically on both the axes and it's a parabola. So y is equal to, this graph you see is y equals to x squared. So my fx is x squared. Is this a function? Well, indeed, this relation is a valid function because, number one, if I give any input, what kind of input I will give to x squared? I can give all real numbers. And I don't have any issue here. If I give a real number, I am going to get a y. So this is a valid function, not just because of that, but it's a valid function because every input that I give, I am going to get a unique y. You can see it in the graph itself. For every x that you put in, you will get a unique y whatsoever. Yes, -2 and +2 can have the same value 4, but that's okay. That 4 is unique for -2 and that 4 is unique for +2. So this relation is indeed a function. It's very important for us to actually analyze which relation is a function and which relation is not. Both, be it a relation or a function, they have three things in common. Every relation and every function, they have a domain. Domain is a set of all inputs that you can take. Codomain is the supporting set where you can find your output. And range is the actual set of output. So whether it's a relation or it's a function, both have something in common, which is that both will have a domain, that is a set of inputs which you can take in, and a codomain, the supporting set essentially, which is a set which would contain the output, and range, is the actual set of output. Both will have that. So the first point was that F has to be a relation. What's a relation? It's a relation is the set of subset of A cross B, the Cartesian product. So hence R, in case R is a relation, is the set of all A comma B, such that A belongs to A and B belongs to B. That means it's a set of all ordered pairs. Similarly, function is also a subset of A cross B, the Cartesian product, where so F also I can say is a set of all ordered pairs A, B, where A belongs to A and B belongs to B. Here the relation is R, so it's ARB. Here the relation is F, so it's AFB. Okay. Now, how to check if a relation is a function? So what was that important thing? Number one, each input needs to have an output. Number two, every output is unique for the given input. So you need to have a unique output, unique y, when y equals to fx. So how to check whether a relation is a function? There are two ways. You can check graphically, And when you check graphically, it is called the vertical line test. When you are using a graph to figure out whether the given relation is a function or not, you use vertical line test. Or else what you can do? You can examine all x values, you can examine all y values. If all inputs are different, then it's a function. If input are repeated, then it's not a function. What do I mean here? Let's look at the two scenarios, y equals to x square and x equals to y square. We've already seen y equals to x square, but to put emphasis on the definition once again, I'm going to take this parabola. So something of this sort. What's going to happen here is, clearly, if you will put input -2, you will get 4. You put input 2, you will get 4. So the inputs are distinct. Even when the outputs are same, inputs are distinct. Every time you have an output, you have a distinct input, okay? But if you create a graph for x equals to y square, so it's going to be something of this sort. So particular x, say x is 1 here. When y is -1, then also I can get x1. When y is +1, then also I can get x1. See, the function is y square, x equals to y square. So there's a difference. When x is 4, say 4 is here, y -2 is also giving you 4, and y +2 is also giving you 4. What's happening? What kind of a relation is this? So what is happening here is that you are getting the same x. You have the same x. X is 4. Y is -2 and 2, which means that you have repeated input and hence it's not a function. And why is it not a function? Vertical line test will make it more clear for you. Vertical line test says that you create vertical lines. In case the vertical line cannot cut the graph at 2 points, then it's a function. And if the vertical lines cut the graph in more than 1 point, then it's not a function. Why? Because in case it's just cutting the graph at 1 point, that means you have a unique output. This point is input and output. Your output is unique. You just have whatever is your x. For this particular x, you just have one output. Suppose this is x1, this is y1, x1 comma y1. But here what is happening, suppose this is x1, now x1 is giving you y1 also and y2 also, which means you are getting 2 outputs out of 1 input, which is a problem. It's not satisfying the definition of function. So that's what vertical line test also tells you. It's basically telling you how graphically you can see whether your definition is getting satisfied or not. Okay? So The first one is a function, but the second one is not. It's very important for you to understand which one is a function, which is not. Let's understand through an example what I mean by saying that you need a unique output. And secondly, that X values, that is the input values, should not be repeated. Now, what you can see here is the relation set R consists of 1, 5, 1, 5, 1, 5, 3, minus 8, 3, minus 8, 3, minus 8. What's happening? I can clearly see that I have repeated X, that is repeated inputs. 1 is getting repeated 3 times. 3 is getting repeated 3 times. So please don't just get confused in the namesake. When I say repeated, it means that it should not happen that for the same input you have 2 outputs. The output has to be unique. 1 is repeated, but it's always coming with the output 5. 1 is always giving you the output 5. 3 is repeated. 3 is giving the output minus 8, always. So hence, this relation set is a function. It is not defying any part of the definition of a function. The relation set 1, 2, 2, 3, 3, 4, 4, 5. What's happening here? 1 is related to 2, 2 is related to 3, 3 is related to 4, 4 is related to 5. So you have different inputs giving you different outputs. Hence, this is also a valid function. If you have the relation set 1, 6, 2, 5, 1, 9, 4, 3, well, I have a repeated X. 1 is getting repeated. And this time, 1 is not giving the same output. So 1 is giving 6 and 1 is also giving 9. So it's a scenario where the same input is giving you 2 output. That means output is not unique. No unique output. So that's a problem. Hence the conclusion, all functions are relations, but not all relations are function. To be a function, there is some more restriction that needs to get satisfied by that particular relation. Sometimes it's fairly easy for us to actually visualize a function in terms of a mapping. Function is a mapping. You're mapping elements of set A to elements of set B. What kind of a mapping is a function? Where every element of A, which is the set of inputs, is mapping to a unique output in B, which is the codomain, that is the supporting set. Now here what is happening? You have an input which is getting mapped to 3 entries. So do you think we have a unique output? No. Or in other words, we have repeated inputs. There lies a problem. For different outputs, we are getting the same input. This kind of a mapping is one to many because one element is getting mapped to many elements, and this relation is not a function because it is not satisfying the uniqueness part of the definition of function. Yes, all inputs have an output, but some inputs have more than one output, so there's no uniqueness of output, so that's a problem. Here, first thing, do all my inputs have an output? Yes. Are the outputs unique? Absolutely. This seems to be a 1-to-1 mapping. We call it 1-to-1 mapping. And indeed, it is a function because everything in my input set is getting mapped to a unique entry in the codomain. It is a function. What about this relation? Here, everything in the input set is getting mapped. 3 elements in the input set are getting mapped to just one single element. So is it a function? Well, yes, indeed, it's a function. The output is unique. When is the output not unique? When you have more than one outputs for one particular input. But here, this one particular input has this output. So suppose this is X1, it has an output Y1 only. It doesn't have 2 outputs. Input X2 has an output Y1. Input X3 has an output Y1 only. It the inputs don't have more than one output, or in other words, they have a unique image. They have a unique output. Hence, this, which looks like a many-to-one relation, because many inputs are getting mapped to one output, is indeed a function. Thank you.